Okay, so this week we're going to talk about surface water, streams, lakes, rivers, any of that good stuff that we can see water on the surface. This image you're looking at is actually a place called Grand Falls that's here in Arizona. You go up north to Flagstaff and head a little to the east. This is the Little Colorado River, and when there's some water flowing through here, which isn't always, but usually during the spring, when there's some runoff, or during monsoon season, you can get some water flowing down the little waterfall here. It looks very pretty. Okay, so why do we care about streams? Well, of course, this is where we catch our food and, keeps things alive. We know we need water for that for sure. And of course, for transportation, if we understand how rivers behave, it helps us with knowing how we can move materials up and down rivers and, if the water level is changing and things like that. So it's helpful for transportation, certainly for agriculture because we need that water to grow food. If we talk about some hazards associated with water, right? So we got to understand how it moves, where are places that are good places to build and where are places that are bad places to build. So understanding rivers gives us some information about that. And of course, we also get some energy from it. So certainly here in the West, more so, we have dams that are built across rivers that provide power for us. We have to understand our water because, of course, we don't want it to look like this. So mining and agriculture and how we dispose of certain materials is important to understand. And it does make things look pretty. So certainly water is carving into the rock over long periods of time and creating some beautiful scenery, including the Grand Canyon. And potentially there's water on other planets. And once again, if we understand how water moves here on Earth and some of the features it leaves behind, we can use some of that evidence to suggest maybe there was once water on other planets. All right, so where is the water? Well, good question. So it depends on what water we're talking about, but obviously most of the water is in the oceans. So if we were to look at, the big picture here, roughly 97% of the water on our planet is the ocean water. There's about 2% that's frozen. Of course, that varies. And about 0.5%, if we took all the water, right, that's our lakes, streams, but that's also water that's under the ground. That's also water in the air. But of course, we're not really talking about the oceans this week. And so if we just look at fresh water, so we take out the ocean and say, where's the water? You can see that most of the water is frozen. It is in these ice sheets, right? So Antarctica, Greenland, these places hold a lot of water, fresh water. But we're just looking at surface water this week. So lakes and reservoirs and river water, not very much of our total freshwater budget. It's pretty small. Actually, we're going to talk about groundwater, and you can see groundwater is much, much bigger than surface water that we'll talk about this week. And so it is a very precious commodity. So, of course, understanding it and using it wisely is something we should be doing for sure, right? All right, so how does the water system work here? So the cycle here that we see with water is there's evaporation mostly from the oceans. Why? Because they're huge and they have the most surface area. Of course, there's evaporation on lakes and big bodies of water like that. But a big source of the water is from the oceans that gets evaporated into the atmosphere. And then that gets transported. It's moved around by winds. Eventually, there's a change in some of the conditions, which causes that water vapor to become a liquid. It falls to the ground. And really, basically, it can do a couple things. It can either hit the ground and run along the surface. And that's what we're talking about this week. And so it's going to move along the surface. It's going to enter into lakes or rivers or streams, which will then flow back to the oceans, and then the cycle will start over again. Though there is a portion of the water that hits the ground that will actually sink into the ground and be stored in the ground as groundwater. And that water is also moving underground and is trying to flow back down to a body of water, whether that's a lake or an ocean. So there's motion there. And eventually it'll make it back there, and we have this cycle that just repeats So this is how we kind of move water around our planet. And so what we could say is when we have water that hits the ground, it really is going to move along the surface in two ways. It is either going to be what we call sheet flow or channel flow. So most of the things we see would be channel flow. Channel flow means it's in a river, okay, or stream or a brook or whatever we're going to call it, but it has a channel. It has sides and a bottom, and it's funneling the water in a specific direction. Sheet flow is when there is no channel established and it's just flowing across the surface. Best example I can think of that is if you've ever been out and there's been a big rainstorm and it hits like the parking lot, it flows as one big sheet across the parking lot, down slope where there's no defined channel. This is sheet flow. Of course, this happens in nature too, but eventually that sheet flow kind of gets funneled into a channel and then it makes it into a river and then it moves on downstream. And so when we have runoff and we want to say, well, how much, where's that water going and, how much water are we going to get into our stream? Some of these things are useful, of course, for predicting flooding and things like that. Certainly, it's dependent on how much rain is falling, and that's a factor of how hard it's raining and how long it rains. And so that's going to contribute water to our system. The amount of soil or vegetation that is on the ground is going to impact how much water stays on the surface. So if we use our parking lot example, remember, if it hits a parking lot and there's no soil or vegetation, absolutely zero is going into the ground. All of it stays on the surface and we get a lot of water into our stream. And let's say, out in the middle of nowhere, there's thick soils and lots of vegetation, we're going to absorb a lot of that into the ground. So less will flow on the surface. And so when we have flooding problems, sometimes it's attributed to urbanization, where we have covered a lot of the surface with concrete, and so that pushes more water into the system, which can then cause water levels to rise quicker. Whereas in the wild or in nature, before there's been some urbanization, there's a balance here where huge rainstorms don't cause massive floods because a lot of it gets soaked into the ground. And then, of course, finally, how steep the ground is. If you rain on a very steep surface, if there is a lot of soil, if it's moving super fast, not as much gets absorbed and more stays on the surface and gets into our channel. So that's how the slope kind of affects how much water we're getting into our system here. And so when we talk about streams, remember that's the channel. That's what we're kind of referring to there with that statement. And so when we talk about rivers, we say that all of our rivers here are flowing from some starting destination to what we're going to call base level. And that's the end of the stream. And now the end of a stream could be a lake. The ultimate, of course, is the ocean basins. Or you could have one stream merge into another. And if we're defining just that one stream, it would begin at somewhere in the mountain somewhere, and it would end where it merges into the other stream. And for that, just that particular stream, the base level would be where it enters into the other river. Or for a river that empties into the lake, the base level, which is the lowest level it's trying to get to, is where it enters into the lake. And that's going to come into play when we talk about how rivers evolve and how fast the water moves, because base level is the bottom, and of course the top is somewhere where the stream is first being formed. And the difference in elevation is going to dictate how fast the water moves in our stream. And so we talked about why that's important. There are some stages that we'll mention about how the river develops over time. And so, streams grow and change. And so at one point, no stream, and then we have to develop one. And so there's these young streams, and there's features of those that we can use to identify them as young. And then there's mature streams, and then there's these very old streams. And then occasionally we can get streams that have been rejuvenated, something that caused them to look young again. Some of the features of a youthful stream come back under certain conditions. And so we'll look at that as we move through the PowerPoint here. So we're going to talk about our typical kind of stream here, because of course, like everything we talk about, there's exceptions to the rule, for sure. But one of the things we want to talk about is where's all the water coming from that goes into my stream. And so we're going to define that area as a drainage And so some drainage basins are small, some are big, and it depends on what stream we're talking about. And so some of the images that you see here, I know this one's not super big, but like the Mississippi River has an enormous drainage basin. It's draining a ton of the U.S. that is east of the Rockies. Now, it's not all coming from one river, right? There's the Missouri, the Ohio, they're all flowing into the Mississippi, but eventually it does make it into the Mississippi. So the drainage basin for the Mississippi is enormous. But we could look over here at the Colorado River. And so this outline here is the drainage basin for the Colorado River. Every drop of water that falls in this area will eventually make it to the Colorado River. Now, it might not flow down the Colorado through the Grand Canyon. It might come from other places, but eventually those all end up in the Colorado and then out into the Gulf of California. So we define these drainage basins as the water that's entering whatever river we're trying to identify. And so it might look something like this. Here's the Fox River, has some tributaries to it, but we would argue that every drop of rain that fell onto the surface here would eventually make it into the Fox River, and then the Fox River is going to flow into the ocean. So this would be the drainage basin that I could outline for the Fox River. And how is it defined? It's usually elevation. So why is rain that falls outside of this dashed line not going to the Fox River? Probably because it looks something like this image. There's a ridge or a high zone at high elevation that when water falls on one side, it flows to the left. If it falls on the other, it flows to the right. So I have two river systems, two drainage basins that are separated by a divide. So usually the mountainous areas or ridges are dividing different basins, which then gives us these different river systems, right? So if we know something about how big the drainage basin is, then we can know how much water comes into the river system. And that can be useful for predicting floods or how much water we can use if we're going to be taking water or damming water or making reservoirs. So understanding how much water the system gets can be useful. And then if we look at how the parts of a river, we would argue that there are the headwaters. These are the very beginning of the stream. And so usually it's up in a high elevation area. And the features that we see in the headwaters differ from the plains area, which differ from the delta. So remember, base level is the lowest point along this whole system. And so the headwaters are the high elevations. The base level is where it dumps into a body of water, and it can't go any lower than that. Okay, so the difference in elevation gives us how steep the river system is. But typically what we see is it's steeper up here in the mountains, and then the gradient, which is a term we'll introduce in just a second, changes from steep, kind of medium, to very flat as it gets to the end of its kind of system here, right? So we're going to look at some features of these different things. And the delta is a deposit part of the system where all the material that's being transported gets deposited because we've ended our river system, the velocity in the stream goes to practically zero, and we dump anything and everything that the river is hauling along. And so we get deposits there. So this is just parts of the river system. And so you want to be able to identify those by some of the features that we see. So we'll go into those in a second here. So some of the terms that we want to associate with the different parts of the river is something called gradient. And basically that's the slope or how steep the stream is. Usually that's measured in, we do the metric system, it's meters per kilometer. But here in the U.S., the most common thing you'll hear is feet per mile. Velocity is the speed, right? Distance traveled per time. And so you would hear, meters per second. So something, or feet per second. You can use something like that to give us a speed. And it varies. The velocity varies, of course, depending on the gradient. If it's very steep, we have a high velocity. Not very steep, we have a lower velocity. And some other factors influence the velocity, some friction and things like that. The shape of the stream also affect that. And then discharge is the amount of water, a volume. So this is usually given in meters cubic meters per second or cubic feet per second, right? So like a box, a cube, because we're talking about length, width, and depth kind of thing, right? And so that can tell us something about water and how much is moving through the system. So if we look at gradient, what we see is we can measure it over the entire system from the head of the river system and the headwaters to where it ends at the base level. And so if we knew the elevation here, which technically would be 0 because it's the ocean, sea level, and we could get the elevation here, and then we'd figure out how far does it travel. And the distance would tell me we have the vertical drop, what's the elevation change, divided by the distance. And like I said, here in the U.S., we would get feet per mile. And so typically that would be the overall gradient. But we could say, what is the gradient up here in the mountains? It would be really high. We would have hundreds of feet per mile. And then out here, it would maybe be, in the 20s and 30s. And then out here, where it's much older part of the stream, it would probably be in the 2 to 3 feet per mile. Okay, so it changes as the stream moves downslope to its ultimate ending, which is in this case the ocean. And so in places where it's young and in the headwaters, this is where we get these hundreds of feet per mile. And they look something like this. We have rapids because the stream's moving quickly because it's very steep. We have waterfalls, we have high erosion rates. It tends to be a straighter part of the system because it's moving very quickly. And then as we move down into the older parts of the stream that are farther from the beginning, we get these, couple feet per mile. So think Mississippi River, right? This would be down here where it's close to the oceans here. So sometimes it's almost imperceptible to see how steep it is. But it's enough, right, to move it in one direction. As long as it's just a couple feet of gradient or feet per mile, it's going to be moving in one direction. This case, this is what it looks like. So we don't have big rapids. We don't have waterfalls and steep cliffs. We tend to get wider rivers, and we tend to get these rivers, and the term we're going to use here is meander. They're not very straight. They kind of wander around back and forth. Okay, so velocity. Where do we see velocities? Well, we said that in the upper parts of the stream, velocities are high because it's steep. Okay, and then in the lower parts of the stream, they're not as high because it's not very steep. You can also argue that the velocity changes depending on where you are in the stream. So if the stream is relatively straight, the highest velocity is in the middle and kind of near the surface, because as we move away from that zone, we get closer to the riverbed, which is causing friction, which slows down the velocity of the water. Now, around a bend, that's not always the case. And this is important because when we have these bends in the river, it moves the velocity around, the highest velocity. And remember, when we're talking about material, sediment, sands, gravels, muds, that the river has the capability to move, that when the velocity is high, it can move a lot of material. But when the velocity drops, it starts to get rid of stuff. So what we see is high velocity is eroding part of my stream, and low velocity is depositing in my stream. And so what I see is on the outside bend of a river system is the highest velocity. And this is where I erode material. And on the inside bend is where I tend to deposit material. And so these are rivers that are curved like this, right? So a subtle curve wouldn't be as dramatic, but the bigger the curve, the more the velocity shifted. So this higher velocity is on the outside, and it starts to increase velocity on the outside, and it can eat away at that bank, sometimes called a cut bank. And on the inside, the velocity drops, so anything that the stream is carrying gets dumped there, and we get what's called a point bar. We get growth on the inside bend, sand and gravel and silt deposits, which can lead to enough material to be land, and we can shift our river around. And so when we look at stuff like this, this is kind of the example here: erosion on the outside, deposition on the inside. So this is what my river might have started like, but over time, the bend will increase because I'm eating on this outside end here. I'm pushing my river to the right up here. and I'm adding on the inside, so it's moving my river. So over time, these meandering streams will change position, and the meander, or the bend curve, will increase, get bigger and bigger, and we'll get a shift in the position of the river system. And this happens in these meandering river systems, right? These older parts of the stream where it's much more dramatic. This is a lateral erosion. It's eroding side to side, right? Left to right. And so another example of that we see is something like this. So outside bend erosion, right? Outside bend erosion, inside bend deposition, right? So we get this point bar as deposition, we get this cut bank as erosion. All right, there's more you say? Of course. So, and then discharge really fast just to show you what that meant, even though we just talked about it. So discharge is a measure of the amount of water that moves through the system, and it's given in cubic feet per second, right, which is a cubic foot, right, a cube that's a foot by a foot by a foot. And so values like that can give us the amount. So floods a lot of times are measured in cubic feet per second. And to give you an example of stuff like that, we would say that for these huge river systems, like the Mississippi River, 600,000 cubic feet per second would mean if I was standing next to the stream and I counted 1/1000, 600,000 cubic feet of water just went by me. Okay, so 600,000 cubes, a foot by foot by foot, just went by in 1/1000. For the Amazon, 7 million, right, in 1 second. So these are huge values. The Colorado River is putting out, 20 to 30,000 feet per second during huge high flood discharge times, like up in the Grand Canyon, maybe 70, 80,000. And then low water is like 5, 10,000. That's pretty low, just to give you an idea of discharge amounts. And so when we talk about strictly erosion, remember, we said that this meandering, this kind of shifting of the velocity to the outside bend, is causing erosion laterally on the outside bend of a river. But upstream, where the velocities are really high and the gradient is steep, we don't get this side-to-side motion so much. We get a down cutting. So young streams with steep gradients are down cutting, right? So they are cutting vertically. And so young streams tend to be V-shaped, right? So they have this steep-sided shape here. And that's because the river is moving quickly and the energy is focused downward. So even though there's little curves here, and yes, there's some erosion on the outside bend of this river, but most of the energy is focused downward, and we're cutting down into the rock beds or soils or whatever it's cutting down into. And so this is how these rivers that are young, upstream rivers with steep gradients, this is how they're eroding. Okay, they're down cutting. And so we can sometimes see in extreme conditions these slot canyons that form. This is where there's super steep gradients. And if we jump back to that story of that was the young, steep ones, here's the older parts. This is a better picture to show you how streams evolve over time. So you start at A, we go to B here, we see that the outside bend is eroding. It's shifting the river, right, left and right here, and then it keeps going to the point where it's so extreme that a large river might actually flood and break across here, and then it would abandon this part of the system, and this would be a lake. And so this is one of the features of these older river systems that have very low gradients, is that is something called an oxbow lake. It's an abandoned meander bend. And so I think on the main page there's two little animations. One of them shows the formations of these oxbow lakes, so you can take a look at that. The animation's pretty good for that one. And so this is that lateral erosion. So remember, low gradients, this is what's happening. We get meanders, we get movement of the river over time, and then we get erosion on the outside bend, deposition on the inside bend. Oops. Oh yeah. So here's an example. So look, here's an outside bend of a river at time 1. And so under high water conditions, let's say there's a little bit of a flood, the current ate away at the outside bend of the river here. okay, and it removed that material in a short amount of time because it was a big event, right? A very steep, or a lot of water moved through here, right? So you don't want to build your house definitely on the outside bend of a river. Okay, there's more. So how do we move material here in streams? And so there are three ways that streams can move material. And so this has nothing to do with old, young, or steep or not. The three places that it can move it is something called the bed load, which is material that's being moved in contact with the bottom of the channel, the bed of the channel. Usually this is the heavier stuff. You can roll stuff or slide stuff or bounce it, but it's in contact with the bed of the channel. We call that the bed load. There's material that's small enough and light enough to be suspended. We call that the suspended load. Those are the smaller particles that are floating in the river that don't make contact with the bottom of the bed. And then there's some portion that is actually dissolved within the water that you can't see. And so this is how the three ways that rivers move material. And so how do they deposit? It's usually just a change in velocity. So at a certain speed, I am moving material, and when water levels drop or speed changes, then I start depositing stuff. When it increases velocity, I start eroding stuff. So it's a common thing that's happening in river systems. They're eroding and depositing, eroding and depositing. A lot of deposition is happening during flood events. And so this is where we have these material being moved because there's a lot of energy, and then the flood dissipates and it drops all that material. And we get a lot of deposition during that time. And then during the normal, flowing of the river system, we can get deposition and erosion kind of back and forth. And sometimes it looks like this. You look at that as a deposition, you're like, I don't even know what that means. It doesn't look like anything. But the fact that there's larger pieces and they're rounded. Rounded pieces are a great indicator of rivers because material has been tumbled along the river bed and all the sharp edges have been rounded and the material is being rolled along the bottom of the bed. And so rounded pieces, a variety of big and small, this kind of tells me that water moved this material. When there's a lot of larger gravels, we would argue it's probably somewhere near the channel, the main energy, where the highest velocity is, because it can move the bigger stuff, right? And the smaller pieces are where the velocity is lower. So we said that we're depositing as we decrease velocity, and of course, if I haven't told you about a term, alluvium is material deposited by a stream, so we might throw that out here. And I just want you to make sure you're aware of that. And so a few of the features that we haven't talked about yet. So certainly rapids and waterfalls are features that are common with very high gradient streams. When we get to now lower streams, we have a few more features, but of course a channel is common in both high and low, but this is still a higher velocity zone. And so if we were looking at sediment or a rock, we would be looking for things made up of sands and gravels. Because they're bigger, it takes more energy to move them. And so those are an indicator of a channel deposit. And if we move down to some other smaller things, we would get a feature that we see on rivers called levees. Now this is once again not in these really high gradient areas. These are these lower gradient areas. You start to develop this meandering stream that potentially floods over time. And so during a flood, the river overtops its channel. It brings some material with it. It deposits a lot of material right on the edge because there's a very big velocity drop when the river is no longer constricted by the channel. It overtops it. It deposits a lot of stuff right on the edge and forms what's called a natural levee. This can be anything from gravels, sands, and muds. And then the water flows out into what's called the floodplain out here. And here the velocity eventually goes to zero, and the very fine stuff ends up out there. So levees form along the river edge here. They're gravel, sands, and muds from floods. And then floodplains are usually these very small pieces, muds and silts, and this is because when we overtop the channel, the velocity eventually drops to very low or eventually non-existent, and all the mud pieces, the really tiny things, settle out. And they fill in this valley, and this is why people farm here, because it's really good material to grow food in. All right, I'm going to race through the last couple. A terrace. What the heck's a terrace? Okay, so look, what we can get is a change in base level. What does that mean? Well, remember, base level is a low point. And so if we move up and down, we can cause the river to change from eroding side to side laterally to eroding vertically up and down. So the steeper, the more energy is going down. So in the picture you're seeing here is a typical older stream, very low gradient. It's starting to meander. It has flooded this valley a lot and filled in the valley with lots of muds over hundreds and thousands of flooding events over long periods of geologic time. But what if we uplifted this area? We know that plate tectonics is causing things to crash together and we get big uplift events. What if we made this higher? Now the ocean level is still the same, but I've increased my gradient, made it steeper. It wants to down cut now, my river does, and it starts to cut into its own deposits, the floodplain deposits. And so it'll do that until it gets back to the same level it used to be. So in this second picture, the velocity has increased, the gradient has increased, and so the energy to down cut has increased, and I start to cut down. But then, as it cuts down, it goes back to the same gradient it was before, where it was pretty small or pretty low. And so now it starts cutting side to side. And I end up with this little bench here called a terrace. In some places, you can have multiple bench steps, which just shows that the river system has slowly been cutting down as of late. And so it was nice and flat and pretty low and meandering, and there was some event that caused the land surface to rise up. Or, of course, we could have base level lower. So if the ocean basins lowered for some reason, it would also increase the gradient and cause the down cutting and give us these terraces, okay, which tell us something about elevation change of the land surface. We did mention in that one little picture meanders, right? This is this winding of the river around, but that term oxbow lake, remember, refers to these little cut-off meanders that as they become extremely meandering, a little event where there is a little more extra water caused it to break through and then change its course and abandon this loop. And some water stays in there and it becomes a lake, and we call that an oxbow lake. Once again, these are features associated with very low gradient older stream systems. And then finally, we get delta deposits. This is all the material that gets deposited at the very end, where the river takes all of the material and dumps it into an ocean or a lake, and we get just tons of sediment deposited here. And here's a tiny one where this little tiny river is emptying into a stream, but here is an example of the Mississippi River Delta that's dumping into the Gulf, and we get huge amounts of sediment. So the Nile, of course, a huge river, and the Mississippi are dumping tons and tons of material into the oceans here. And eventually it becomes land, and of course then we live on it. And so we see that certainly in New Orleans, which exists right here, is built on delta deposits. So all this material was deposited by the Mississippi River over long periods of time, and it's as the river has moved around. So remember, this meandering and moving of the river, it's causing it to fill up this area of sediment back and forth. So at one point, Mississippi dumped material here, and it developed a very big delta here. There was lots of flooding, and so it flooded back and forth, and it nourished the floodplain. And we had this growth here. But then the river abandoned its loop and started to deposit other places, and it spread out the delta over time here. And of course, today it goes way out here. And in theory, it would probably like to abandon and go here again. But of course, we don't want that to happen because we use this route for transportation to bring all materials up Mississippi. And if it went this way, all this industry would go away. So the natural process is to abandon and create a new delta, but we won't let that happen because we've kind of become entrenched in there. And just to give you an example of that, here's a profile of New Orleans where it sits between the Mississippi River and Lake Pontchartrain. It's below sea level because all this deposit of delta material and flooding that's happened over the past 10,000 years has built up that as land surface. But no more flooding, because why? Our cities live there. No more changing of delta, because our cities are there. And so all that loose material is sinking, compacting over time. And so we had to build these huge levees so New Orleans doesn't flood every day. And of course, that's why when Katrina came along, it was bad news. Bad news bears, because they live below sea level. Okay, and I know I've meandered longer than ever for this one, but if we look at something like this, which we do see in Arizona, you're seeing a little bit of contradictory evidence. I see meanders, which means old streams, but meandering streams should have levees and big flat floodplains where there's lots of agriculture. But here I see meanders, which tells me very old, but I see super steep V-shaped canyons, which tells me very young. So how do we explain something like this? This is what we talk about when we use the term a rejuvenated stream. What's happened on the right here is it used to look like the left. This was an old river system that was meandering like this. But there was a huge amount of uplift here, very fast. And the river system did not have time to adjust, and it started to just cut down in the shape it had already formed. It got super steep, meant the velocity increased, which means most of the energy went cutting down, and it locked in this meander as it cut down extremely quickly. And so once again, there's some evidence here to suggest that there was some uplift in this area, that this area used to be pretty broad and flat, and probably close to sea level. But some event caused an uplift to occur and downcutting, and we trapped these meanders within this rock, and so we get this beautiful incised meanders, as they're called, and that's what I got for you. All right, sorry it's so long, and I was, watching some of the dictation down here that PowerPoint's doing, and there's definitely some mistakes, so be wary if you're focusing only on the dictation that PowerPoint is giving you. All right, as always, if you have questions or if I've just confused the heck out of you, please don't hesitate to contact